Right now, somewhere in our galaxy, there is a dead star no wider than a city, once born spinning hundreds of times per second, wrapped in a magnetic field so powerful that if you placed it halfway to the moon, it would erase every credit card on Earth. And every once in a while, without any warning, the surface of that star cracks open. What follows is a burst of energy so violent that in 1/10 of a second, it releases more energy than our sun produces in 250,000 years. It's called a Magnetar flare, and what's terrifying is that we've already been hit by one. The radiation arrived in 2004 and physically compressed Earth's magnetosphere. Tonight, we're going to explore exactly what happens inside one of these events and why. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with a question that might seem straightforward, but actually leads somewhere extraordinary. What happens when a star dies? You probably know the basic answer. A massive star runs out of fuel, its core collapses, and it explodes as a supernova. That explosion is one of the most violent events in the universe, briefly outshining an entire galaxy. But here's what most people miss. The explosion is not the end of the story. It's the beginning of something far stranger. Because after the outer layers of the star have been blasted into space, after the shockwave has ripped through the surrounding gas and dust, something is left behind at the center. Something small, something incredibly dense, something that shouldn't really exist according to the physics we experience in everyday life. What's left is a neutron star. Now, a neutron star is not like anything you've ever encountered. It's not like a planet. It's not like a normal star. It's not like anything on Earth. A neutron. Star is what you get when you take an object more massive than our sun, somewhere between 1.5 and about 2.5 times the mass of the sun, and you compress it into a sphere roughly 12 miles across. 12 miles. That's about the distance from one end of a city to the other. You could drive across a neutron star in maybe 15 minutes if there were a road. And yet, that tiny sphere contains more mass than our entire sun, which itself is over 300,000 times more massive than Earth. Think about what that means. Take the sun, every bit of it, all 864,000 miles of diameter, all 1.3 million Earths worth of volume. Now crush all of that mass into a ball the size of Manhattan. That's a neutron star. The density is beyond anything your mind can properly visualize. A single teaspoon of neutron star material would weigh about 4 billion tons on Earth. 4 billion tons in a teaspoon. That's roughly the weight of every car, truck, bus, and train on the planet combined, compressed into a volume smaller than a sugar cube. If you dropped a teaspoon of this material onto Earth's surface, it wouldn't just sit there. It would punch through the ground like a bullet through wet tissue paper. It would fall straight through the crust, through the mantle, through the core, and out the other side. Nothing on Earth has the structural integrity to support material this dense. Nothing even comes close. To really grasp what we're dealing with, let's think about that density another way. Mount Everest, the tallest mountain on Earth, has a mass of roughly 161 billion tons. A teaspoon of neutron star material at 4 billion tons is impressive by any standard, but even it is dwarfed by that mountain. Yet the neutron star packs that teaspoon's worth of mass into a volume you could hold in your hand, and the entire star contains more mass than the sun, And a neutron star is made entirely of this stuff, 12 miles of it in every direction. The total mass is roughly 1.5 to 2 times the mass of the Sun, packed into a volume so small that if you placed a neutron star next to any major city on Earth, the star would fit comfortably inside the city limits. The reason neutron stars are so dense comes down to what happens during the collapse. In a normal atom, you have a nucleus made of protons and neutrons surrounded by a cloud of electrons. Most of the atom is empty space. The electrons orbit far from the nucleus relative to their size. If you scaled up an atom so that the nucleus was the size of a marble, the nearest electron would be about half a mile away. Atoms are overwhelmingly empty, but in a neutron star, gravity has crushed the atoms beyond recognition. The electrons have been forced into the protons through a process called inverse beta decay, turning the protons into neutrons and releasing a flood of particles called neutrinos. What remains is matter composed almost entirely of neutrons packed together so tightly that there is essentially no empty space between them. The matter has reached what physicists call nuclear density. It's the same density as the nucleus of an atom, but now it's not a tiny speck at the center of an atom. It's a sphere 12 miles across. You've essentially turned an entire star into one enormous atomic nucleus. This compression gives neutron stars some astonishing properties. They rotate incredibly fast. When a star collapses, conservation of angular momentum means the smaller object spins much faster than the original star. Just like an ice skater pulling in their arms spins faster. A star that rotated once every few weeks can become a neutron star spinning hundreds of times per second. Some neutron stars, called millisecond pulsars, rotate over 700 times per second. The surface of such a star is moving at a significant fraction of the speed of light. If you were somehow standing on the equator of a millisecond pulsar, the surface beneath your feet would be whipping around at tens of thousands of miles per second. You would be flung off instantly, except that the gravity is so intense, you couldn't be flung off. The gravitational pull at the surface of a neutron star is roughly 200 billion times stronger than gravity on Earth's surface. If you could somehow survive the radiation and the heat and the magnetic field long enough to fall toward a neutron star, by the time you reach the surface, you would be traveling at roughly half the speed of light. The impact would release energy equivalent to a nuclear weapon, and that's just from your body falling. Neutron stars also have magnetic fields. All stars do. The Sun has a magnetic field. Earth has a magnetic field. But when a star collapses into a neutron star, its magnetic field gets compressed along with everything else. And because the field strength increases in proportion to the square of the compression ratio, a modest stellar magnetic field becomes enormously powerful in a neutron star. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. That's already extraordinary. Earth's magnetic field is strong enough to deflect the solar wind and make compass needles point north. A neutron star's field is 1 trillion times more powerful than that. But some neutron stars have magnetic fields that are far, far stronger even than this. And this is where our story truly begins. Because among the population of neutron stars scattered across the galaxy, there exists a rare and terrifying subclass. These are the magnetars. A magnetar is a neutron star with a magnetic field roughly 1,000 times stronger than a typical neutron star. While an ordinary neutron star might have a magnetic field of about 1 trillion Gauss, a magnetar has a field of about 1 quadrillion Gauss. 1 quadrillion. That's a 1 followed by 15 zeros. To put this in some kind of perspective, the strongest continuous magnetic field ever produced in a laboratory on Earth is about 450,000 Gauss. A Magnetar's field is more than 2 billion times stronger than the most powerful magnet humans have ever built. Earth's own magnetic field, the one that shields us from the solar wind and makes compasses work, measures about half a Gauss at the surface. A Magnetar's field is roughly 2 quadrillion times stronger than the field protecting our planet. The difference between Earth's magnetic field and a Magnetar's is proportionally larger than the difference between the width of a single atom and the distance from Earth to Jupiter. At closer range, the numbers become even more absurd. If you placed a Magnetar at half the distance from Earth to the Moon, roughly 120,000 miles away, its magnetic field would be strong enough to erase every credit card on the planet. Every magnetic stripe on every bank card, every hotel key, every piece of magnetic storage, media would be wiped clean. From a distance of 120,000 miles. At a distance of about 600 miles from a Magnetar, the magnetic field becomes so intense that it would begin to distort the electron clouds of your atoms. The chemistry of your body would break down. Molecules would be stretched into long, thin shapes aligned with the field. Water molecules, the stuff you're mostly made of, would be deformed beyond recognition. You would be killed not by heat, not by radiation, not by gravity, but by magnetism literally pulling your atoms apart. At the surface of the Magnetar, the field is so powerful that it affects the vacuum itself. Quantum electrodynamics, the theory that describes how light and matter interact at the deepest level, predicts that in a sufficiently strong magnetic field, the vacuum of empty space becomes birefringent. That means it bends light differently depending on the direction of polarization. The empty space around a Magnetar acts like a crystal, splitting light into 2 beams. Space itself becomes an optical medium because the magnetic field is strong enough to interact with the virtual particle pairs that quantum mechanics says are constantly flickering in and out of existence in the vacuum. This is not science fiction. This is a prediction of well-tested physics, and there is observational evidence supporting it from studies of isolated neutron stars. So how does a Magnetar get such an extreme magnetic field? Why do some neutron stars become Magnetars while others don't? The answer lies in the first few seconds of the neutron star's life, in the chaos of the supernova that created it. When the core of a massive star collapses, the newly formed neutron star is initially a hot, turbulent, violently churning ball of neutron-rich matter. The temperature is hundreds of billions of degrees. The matter is not solid. It's a fluid, and it's convecting rapidly, with enormous currents of neutron-rich material rising and falling in the interior. If the neutron star happens to be rotating fast enough during these first critical seconds, something remarkable can happen. The combination of rapid rotation and vigorous convection can generate a dynamo effect, the same basic mechanism that produces Earth's magnetic field, but operating under far more extreme conditions. Earth's magnetic field is generated by the motion of liquid iron in the outer core. The motion of electrically conducting fluid generates electric currents, and those currents produce magnetic fields. And those magnetic fields influence the fluid motion, creating a self-sustaining loop. In a newborn neutron star, the same principle operates, but the fluid is not molten iron. It's a sea of neutrons at nuclear density, convecting at enormous speeds. And if the rotation period of the proto-neutron star is short enough, roughly on the order of a few milliseconds, the dynamo can amplify the magnetic field to magnetar strengths in a matter of seconds. The resulting field is so powerful that it actually slows the star's rotation dramatically. A magnetar born spinning hundreds of times per second will be slowed to spinning once every few seconds within 1,000 years or so, because the magnetic field acts as a brake, converting rotational energy into magnetic energy and radiation. This is why magnetars spin relatively slowly compared to other young neutron stars. They were born fast, but their extraordinary magnetic fields stole their spin. Not every neutron star undergoes this process. If the rotation during those first few seconds isn't fast enough, or if the convection doesn't have the right characteristics, the dynamo doesn't amplify the field to extreme levels. The neutron star ends up with a strong but ordinary magnetic field, about 1 trillion Gauss, and lives a quieter life as a regular pulsar, beaming radio waves into space as it spins. It still has an incredibly powerful magnetic field by any earthly standard, but compared to a magnetar, it's mild. The difference between an ordinary neutron star and a magnetar is like the difference between a campfire and a thermonuclear weapon. Both are hot, both produce energy, but they're operating in completely different regimes of power. Only a small fraction of neutron stars, perhaps 1 in 10, become magnetars. There are estimated to be roughly 30 million neutron stars in the Milky Way, but only a few thousand of those are probably magnetars. We've detected fewer than 30 so far, because magnetars are difficult to observe. They don't produce the steady radio pulses that make ordinary pulsars easy to find. They're often dim in radio wavelengths, hiding in the electromagnetic background of the galaxy. Instead, they reveal themselves primarily through their violent outbursts, through the very flares we're going to explore in detail. Now, here is where things become crucial for understanding what comes next. A magnetar is not just a ball of ultra-dense matter with an extreme magnetic field floating passively through space. A magnetar has structure, it has layers, and those layers interact with the magnetic field in ways that are central to everything that follows. The outermost layer of a magnetar is its crust. This crust is extraordinary. It's a crystalline lattice made of neutron-rich atomic nuclei, primarily iron, but with a variety of heavier, more exotic elements, arranged in a rigid structure. Think of it as a solid shell encasing the star. But this is not ordinary solid matter. This is the strongest material in the known universe. The crust of a neutron star is roughly 10 billion times stronger than steel. It can withstand pressures and stresses that would shatter any material on Earth instantly. The reason for this incredible strength is that the nuclei in the crust are arranged in a crystal lattice held together by immense electrostatic forces. Compressed to densities far beyond anything in ordinary solids. The nuclei are packed so close together and the binding energies are so high that the lattice resists deformation with extraordinary rigidity. Deeper in the crust, the nuclei are pushed so close that nuclear forces begin to act between them, creating exotic shapes physicists call nuclear pasta, further reinforcing the structure. The crust is thin relative to the star. It's perhaps only about a mile thick, sitting on top of the much larger interior. But it plays a critical role because the magnetic field lines of the magnetar are anchored in this crust. The magnetic field threads through the crust, emerging from the surface and looping through the magnetosphere. the region of magnetic influence surrounding the star. Wherever the field lines are rooted, they're locked into the crystal lattice of the crust. They can't move through the crust easily. They're frozen in, held in place by the rigidity of the material. Beneath the crust lies the interior, which is a very different environment. The deeper you go into a neutron star, the denser the matter becomes. Just below the crust is a region of neutron-rich fluid, a superfluid in fact. At these densities and temperatures, neutrons pair up and enter a quantum state where they flow without friction, much like superfluid helium in laboratory experiments, but under far more extreme conditions. Even deeper, at the very center of the star, the matter may take on exotic forms that we don't fully understand. Some theories suggest the core might contain a quark-gluon plasma, where neutrons and protons dissolve into their constituent quarks. Others suggest even stranger states of matter. We genuinely don't know what's at the center of a neutron star, and this is one of the outstanding mysteries in physics. What matters for our story is the contrast between the crust and the interior. The crust is rigid, the interior is a fluid. The magnetic field permeates both, but it behaves differently in each region. In the fluid interior, the magnetic field can evolve. It can twist. It can rearrange. The fluid can flow and carry the field with it. Magnetic stresses in the interior can build and change over time as the internal fluid slowly shifts. But in the rigid crust, the field is locked in place. The crust resists any change in the magnetic field configuration. It holds the field lines where they are, even as the interior pushes and pulls on them from below. This creates a fundamental tension. The interior is trying to rearrange the magnetic field. The crust is preventing that rearrangement. Stress accumulates at the boundary between the crust and the interior, and within the crust itself, as the magnetic forces try to move the field and the crystal lattice refuses to yield. It's an almost perfect analogy to plate tectonics on Earth. Earth's mantle slowly convects, driven by heat from radioactive decay deep inside the planet, and the rigid crustal plates resist this motion. Stress builds along fault lines, until eventually the rock fails and the plates slip suddenly, releasing energy as an earthquake. The longer the stress builds, the more violent the eventual release. The same principle holds for magnetars. On a magnetar, the same basic drama plays out, except the forces involved are not geological. They're magnetic. And the energies are not measured in the equivalent of a few megatons of TNT, as with the largest earthquakes on Earth. They're measured in quantities that dwarf the total energy output of the sun. Where an earthquake might release 10 to the 25 ergs, a magnetar flare can release 10 to the 46. That's a difference of 21 orders of magnitude, 21 powers of 10. The gap between the largest earthquake and a magnetar giant flare is staggeringly, almost absurdly vast. This is the setup. This is the loaded gun. A magnetar sits in space, spinning slowly, its crust locked in place, its magnetic field threading through that crust and looping through the magnetosphere above. Deep inside, in the superfluid interior, magnetic forces are slowly, inexorably pushing, twisting the field, building stress in the crust. The crust holds. It's the strongest material in the universe. It can withstand pressures that would obliterate anything else. But even the strongest material has a breaking point, and the magnetic forces inside a magnetar are almost unimaginably strong. The energy stored in a magnetar's magnetic field is staggering. The total magnetic energy is on the order of 10 to the 47 ergs. That's a number so large it's hard to put into context, but let me try. The Sun produces about 3.8 times 10 to the 33 ergs of energy every second. That's an enormous amount of energy by any standard. It's enough to power all of human civilization millions of times over. The total energy stored in a Magnetar's magnetic field is equivalent to the Sun's entire energy output for roughly 10,000 years. All of that energy is stored in the magnetic field, threading through the crust and the interior and the magnetosphere. And some fraction of that energy is tied up in the stressed, twisted configurations that develop as the interior pushes against the crust. The crust is holding back a reservoir of energy that is genuinely difficult to comprehend. And it's all waiting to be released. To appreciate just how much energy we're talking about, consider the most powerful nuclear weapon ever detonated by humans. The Tsar bomber, tested by the Soviet Union in 1961, released about 2.1 times 10 to the 26 ergs of energy. The energy stored in a Magnetar's magnetic field is roughly 10 to the 21 times larger. That's 1,000 billion times more energy than the most powerful nuclear weapon ever built. And this energy is stored in an object 12 miles across. Now, the crust doesn't fail all at once. At least not usually. Most of the time, the stress builds slowly and is released in small increments. A small region of the crust might crack, releasing a modest amount of energy and producing a brief burst of X-rays that we can detect with space-based telescopes. These small events are common. Magnetars regularly produce bursts of X-ray and gamma-ray emission lasting fractions of a second, releasing energies of around 10 to the 38 to 10 to the 41 ergs. These are called magnetar bursts, and they're detected fairly regularly from the known magnetars in our galaxy. They're like small earthquakes on the magnetar's surface, localized events where a small patch of crust shifts slightly, allowing a small amount of magnetic stress to be released. But occasionally, very rarely, something much larger happens. The stress doesn't just build in one small region, it builds across a large area of the crust. Multiple fault lines develop. The magnetic forces become so overwhelming that the crust doesn't just crack in one spot. It fails, catastrophically across a significant fraction of the star's surface. This is the event we're building toward. This is the magnetar giant flare, and when it happens, the energy release is so enormous that it makes the smaller bursts look like candle flames next to a nuclear explosion. But before we get to the flare itself, we need to understand something more about the magnetic field and the crust and how they interact. Because the mechanism of the flare is not just about things cracking. It's about what happens to the magnetic field when the crust finally lets go. And that involves a process that is both beautiful and terrifying. A process that converts magnetic energy into heat and radiation with extraordinary efficiency. The crust is the trigger, but the magnetic field is the weapon. And the flare is what happens when the trigger is finally pulled. You might be wondering how we know any of this. After all, we can't visit a neutron star. We can't put one in a laboratory. We can't drill into its crust or measure the stresses building inside it. And you'd be right to wonder. Much of what we know about the internal structure of neutron stars comes from theoretical physics. From solving equations that describe matter at nuclear density, from computer simulations that model the behavior of fluids and magnetic fields under extreme conditions. But it's not all theory. We have observational evidence too. When magnetars produce bursts and flares, the characteristics of that emission, the timing, the energy spectrum, the way the brightness varies over time, all of these carry information about the physical processes occurring at and near the star's surface. By studying the light curves and spectra of Magnetar bursts, astronomers can test different models of the crust and the magnetic field and see which ones match the observations. And the models that work best, the ones that produce the closest match to what we actually see, are the ones involving crust fracture and magnetic field rearrangement. The physics of the crust, specifically its composition, its breaking strain, and its interaction with the magnetic field, is constrained by nuclear physics experiments here on Earth. We know quite a bit about how nuclear matter behaves from particle accelerator experiments. We can test the equation of state of dense matter, the relationship between pressure and density, using data from heavy ion collisions. And those measurements feed into our models of neutron star interiors. The Neutron Star Interior Composition Explorer, known as NIXA, an instrument mounted on the International Space Station, has been measuring X-ray emissions from neutron stars since 2017. Its observations have helped constrain the size and density of neutron stars, confirming that they're roughly 12 miles across and have the properties our models predict. So while there's still uncertainty, while we don't know everything about what goes on inside a magnetar, we're not just guessing. We're building a picture from theory, computation, and observation, and that picture is becoming clearer every year. What we know for certain is this. A magnetar is a neutron star with an extraordinarily powerful magnetic field, born in the dynamo fury of its first seconds of existence. It has a crust of incredible strength, the strongest material known to exist anywhere in the universe, locked with magnetic field lines that thread through it like steel cables through concrete, and beneath that crust, in the superfluid interior, magnetic forces are slowly, relentlessly building stress, pushing against the crust, waiting for the moment when even the strongest material in the universe can hold no longer. That moment, when it comes, will be one of the most violent events the universe can produce. More energetic than a supernova in terms of energy released per second. Brighter than anything else in the sky for a brief, blinding instant. And it begins with a crack. A fracture in a crystal lattice 12 miles across, 10 billion times stronger than steel, on a spinning dead star thousands of light years from Earth. That is what a magnetar is. A dead star. A cosmic relic of unimaginable density, wrapped in the most powerful magnetic field in the known universe, encased in a crust stronger than any material that exists anywhere else. And now we need to understand what happens in the long, slow buildup before that crack finally comes. Because the flare doesn't happen suddenly. It's the result of a process that takes months, years, maybe decades of accumulating stress. And understanding that buildup is the key to understanding why the flare, when it finally arrives, is so catastrophically powerful. So now we have this object. A neutron star 12 miles across, more massive than the sun, spinning once every few seconds, wrapped in a magnetic field a quadrillion times stronger than Earth's. Its crust is the strongest material in the known universe. A crystalline lattice of neutron-rich nuclei bound together by forces that make steel look like wet paper. And threading through that crust, anchored into its rigid structure like rebar set in concrete, are magnetic field lines of almost inconceivable intensity. Beneath the crust, A superfluid interior churns slowly, carrying magnetic flux with it, pushing against the field configuration that the crust is trying to hold in place. The stage is set. Now we need to understand the slow process that turns this already extreme object into a bomb. The key to everything that follows is a single concept: magnetic stress. And to understand magnetic stress, we first need to understand something fundamental about magnetic fields that most people never think about. Magnetic fields are not just abstract lines drawn on a diagram, they are physical. They carry energy, they exert forces, they push and pull on matter and on each other. A magnetic field is as real as a rubber band stretched between two posts. It has tension along its length, trying to shorten itself, trying to snap back to a simpler configuration. And it has pressure perpendicular to its length, pushing outward, trying to expand. These are not metaphors. These are measurable, physical properties described by precise mathematical equations. The energy stored in a magnetic field is proportional to the square of the field strength. Double the field strength, and you quadruple the energy. This is why magnetar fields are so energetically important. A magnetar's field is about 1,000 times stronger than a typical neutron star's. That means the energy stored in a magnetar's field is about 1,000,000 times greater. A factor of 1,000 in field strength becomes a factor of 1,000,000 in energy. This scaling is not linear, it's quadratic, and it makes all the difference. The total magnetic energy in a magnetar is roughly 10 to the 47 ergs, enough to power our sun for about 10,000 years, all stored in and around an object you could drive across in 15 minutes. Now here is what makes a magnetar fundamentally different from an ordinary neutron star, in terms of what happens over time. In an ordinary neutron star, the magnetic field is strong, about 1 trillion Gauss, but the energy stored in that field is modest compared to the structural strength of the crust. The magnetic forces push on the crust, yes, but the crust is strong enough to resist them comfortably. The magnetic pressure never comes close to exceeding the breaking strain of the crustal lattice. The crust holds, nothing dramatic happens. The neutron star spins, beams radio waves, and gradually slows down over millions of years as it radiates energy. It lives a relatively quiet life. A magnetar is different. In a magnetar, the magnetic energy is so enormous that it becomes comparable to, and in some regions can actually exceed, the elastic energy of the crust. The magnetic forces are strong enough to genuinely challenge the structural integrity of the strongest material in the universe. This is extraordinary. Remember, this is the most rigid material that exists anywhere in nature. The forces needed to deform it, let alone break it, are immense beyond everyday comprehension. And yet, the magnetic field of a magnetar generates forces of exactly that magnitude. The crust is not comfortably holding the field in place. It's straining. It's under siege. It's fighting a battle it can hold for a while, maybe years, maybe decades, but not forever. Let's talk about how the stress actually builds. The process begins in the interior of the star. Remember, the interior of a magnetar is not a solid. It's a superfluid, a quantum fluid of neutrons flowing without friction. And this fluid is threaded with magnetic flux. The magnetic field permeates the interior just as it permeates the crust and the magnetosphere above. But in the fluid interior, the field can move. It can evolve. It's not locked in place the way it is in the rigid crust. The field in the interior evolves for several reasons. One is a process called ambipolar diffusion. Even though the interior is mostly neutrons, there's a small fraction of protons and electrons mixed in, perhaps 5 to 10% by number. These charged particles interact with the magnetic field directly because magnetic forces only act on charged particles, not on neutral ones. The neutrons, being electrically neutral, don't interact with the magnetic field directly. They feel no magnetic force at all. But the protons and electrons do, and as the magnetic field pushes on them, they try to move. As they move through the sea of neutrons, they drag some neutrons along through nuclear collisions, but not all of them. There's friction between the charged component and the neutral component. The result is a slow drift of charged particles relative to the neutral neutrons, carrying the magnetic field with them. This drift, this ambipolar diffusion, causes the internal magnetic field to gradually rearrange itself over time. The field lines slowly migrate, twist, and evolve into new configurations. The process is slow, operating over timescales of thousands to tens of thousands of years, but it's inexorable. It never stops. As long as the magnetic field has internal stresses, ambipolar diffusion will continue to rearrange it, and that rearrangement will continue to load stress onto the crust above. Another mechanism is Hall drift, named after the physicist Edwin Hall. In the crust of the neutron star, the magnetic field interacts with the electron current flowing through the lattice. This interaction causes the field to evolve in a way that's similar to how fluids develop turbulence. Hall drift doesn't dissipate magnetic energy directly, but it can transfer energy from large-scale field structures to smaller-scale ones, creating regions of intense, localized magnetic stress. Think of it like kneading dough. The overall amount of dough doesn't change, but the internal structure becomes more complex, with folds and layers and regions of concentrated pressure. Hall drift does the same thing to the magnetic field in the crust, creating localized hotspots of magnetic stress that can eventually exceed the breaking strain of the lattice. These processes operate on timescales of years to thousands of years. They're slow by human standards, but fast by astronomical standards. A magnetar might build up significant stress in its crust over the course of months or years. The field in the interior gradually shifts, and as it does, it pushes on the base of the crust. The crust resists. The field pushes harder. The crust strains. The field keeps pushing, and the stress grows. It grows quietly, invisibly, deep inside a star that from the outside might appear to be doing nothing at all. If you could somehow watch a magnetar through a telescope during this phase, you might see nothing unusual. The star sits there, spinning slowly, emitting a steady glow of X-rays from its hot surface. But inside, the tension is mounting. The magnetic forces are building toward a breaking point that nothing in the universe can prevent. To visualize this, imagine a thick sheet of ice covering a lake. Beneath the ice, water currents are flowing, pushing against the underside of the ice. The ice is rigid, it holds, but the currents are persistent. They keep pushing day after day, week after week. Slowly, cracks begin to form. Small fractures appear in areas where the stress is highest. The ice groans, it shifts slightly, but it doesn't break, not yet. The currents keep flowing, the pressure keeps building. More cracks develop. The existing cracks grow longer and deeper. The ice is slowly failing, not all at once, but piece by piece, region by region. And then one day, in one critical spot where the stress has been building the longest and the ice is weakest, the ice finally gives way. A large section breaks free, and everything that was being held back rushes through. This is essentially what happens on a magnetar, except that instead of water currents, we have magnetic forces. Instead of ice, we have a crystal lattice 10 billion times stronger than steel. And instead of the mild energy of flowing water, we have magnetic energy equivalent to 10,000 years of solar output. The physics is analogous, but the scale is beyond anything we encounter on Earth. Now, there's something subtle and important about how the stress builds that many descriptions of magnetars overlook. The stress doesn't build uniformly across the entire crust. It builds preferentially in regions where the magnetic field has the most complex geometry, where field lines are most twisted, most tangled, most distorted from their lowest energy configuration. The magnetic field naturally wants to be in its simplest possible state, which for a magnetar would be roughly a dipole, like a bar magnet with a north pole and a south pole. But the processes in the interior, the ambipolar diffusion and the Hall drift, continuously inject complexity into the field. They create multipolar components, regions where the field loops and twists in complicated patterns. These complex regions store more energy per unit volume than the simple dipolar field, and they exert more stress on the crust per unit area. So the stress concentrates in specific locations on the star's surface, forming something analogous to fault zones on Earth. Just as earthquakes on Earth tend to occur along plate boundaries where tectonic stress is concentrated, the fractures on a magnetar tend to occur in regions where the magnetic field geometry is most complex and the magnetic stress is highest. There's another factor that contributes to the buildup of stress, and it has to do with the magnetar's rotation. As I mentioned, magnetars spin typically once every 2 to 12 seconds. That's slow compared to many neutron stars, but it's still a rotation. And as the magnetar spins down, losing rotational energy to magnetic braking, the shape of the star changes very slightly. A spinning object bulges at its equator due to centrifugal force. As the spin rate decreases, the centrifugal force decreases, and the star wants to become slightly more spherical. But the crust, being rigid, resists this change in shape. It was formed when the star was spinning faster, and its shape reflects that earlier, faster rotation. As the star slows down, the crust is slightly too oblate for its current spin rate. This mismatch between the crust shape and the shape the star wants to have creates additional stress in the crust, a kind of global background tension layered on top of the localized magnetic stresses. It's a relatively small contribution compared to the magnetic stress, but it's there, adding to the total stress budget, tipping the balance in regions that are already approaching their limits. Over time, this rotational stress can push regions that are already close to their breaking point over the edge. We can actually observe evidence of this stress buildup indirectly. Magnetars don't just produce flares at random with no warning. In many cases, a giant flare is preceded by a period of increased activity. The magnetar starts producing more frequent, smaller bursts in the weeks or months before the big event. The X-ray luminosity of the star increases. It becomes restless, agitated, releasing puffs of energy more and more often. It's like the small tremors that sometimes precede a major earthquake on Earth. The foreshocks that indicate stress is reaching critical levels along a fault line. Seismologists have long known that patterns of small earthquakes can sometimes signal an approaching large one. The same principle appears to apply to magnetars, though predicting exactly when the large event will come remains impossible with current understanding. Astronomers have noticed this pattern in several magnetars. SGR 1900 plus 14, for example, showed increased burst activity before its giant flare in 1998. SGR 1806-20 showed a similar pattern of escalating activity in the months before its record-breaking flare in 2004. This pattern makes physical sense. As stress builds in the crust, small regions fail first, producing small bursts. These small failures redistribute stress to neighboring regions, potentially bringing them closer to failure. It's a cascade effect. Each small fracture loads more stress onto the surrounding crust, making the next fracture more likely. The bursts come faster and faster, closer and closer together, as the crust approaches a state of critical instability. And then, when enough stress has been redistributed, and enough small fractures have weakened the lattice, a large-scale failure becomes inevitable. Let me give you a sense of the magnetic pressure involved, because the numbers are genuinely staggering. The magnetic pressure at the surface of a magnetar with a field of 10 to the 15 Gauss is roughly 4 times 10 to the 29 dynes per square centimeter. If you're not familiar with those units, let me convert to something more intuitive. That pressure is equivalent to about 4 times 10 to the 23 atmospheres. Earth's atmosphere, the pressure you feel right now pushing on every square inch of your body, is 1 atmosphere. The pressure at the bottom of the deepest ocean trench on Earth, the Mariana Trench, is about 1,100 atmospheres. The pressure at the center of the Earth is about 3.5 million atmospheres. The magnetic pressure at the surface of a magnetar is roughly 100 quadrillion times the pressure at the center of the Earth. 100 quadrillion. That's the force that the magnetic field is exerting on the crust, pushing it, straining it, trying to rearrange the field lines anchored within it. And this is just the pressure at the surface. Deeper in the crust, where the field might be even more tangled and concentrated, the local magnetic stresses can be higher still. The shear stress, the sideways component of force that tries to slide one layer of crust past another, is what actually causes fractures. When the shear stress exceeds the shear modulus of the crustal lattice, the crust breaks. The shear modulus of neutron star crust material has been calculated from nuclear physics models and is roughly 10 to the 30 ergs per cubic centimeter. That's extraordinarily rigid. But the magnetic shear stresses in a magnetar can reach comparable values. The magnetic forces are genuinely competing with the structural integrity of the strongest material known to exist. This is what makes magnetars unique. In no other object in the universe do we see magnetic forces that can challenge the structural limits of nuclear matter. No other class of star, no other astrophysical environment produces this particular combination of an ultra-strong magnetic field anchored in an ultra-rigid crust. It's this combination, and only this combination, that leads to the phenomenon of magnetar flares. There's one more aspect of the stress buildup that we need to discuss, and it involves the magnetosphere, the region of magnetic influence above the star's surface. Because the stress doesn't just build inside the crust, it builds in the magnetosphere too. The magnetosphere of a magnetar is not empty. It's filled with magnetic field lines that arch up from the surface, loop through space, and return to the surface at another point. These field lines carry energy and exert forces, just like the field inside the star. And as the internal processes twist and shift the field at the surface, those changes propagate upward into the magnetosphere. If the field at the star's surface becomes more twisted, the field in the magnetosphere becomes more twisted too. The magnetospheric field lines get wound up, coiled, stressed, loaded with energy like a spring being compressed. This is critically important because when the crust finally breaks, it's not just the energy stored in the crust that gets released, it's also the energy stored in the twisted magnetosphere above the fracture zone. And the magnetospheric energy can be enormous, comparable to or even exceeding the energy stored in the crustal stresses themselves. Think of it this way. The crust is like the latch on a spring-loaded door. The spring is the magnetosphere, loaded with energy, held in its stressed configuration by the rigid crust beneath it. When the latch breaks, when the crust fractures, it's not just the latch that releases energy, it's the spring. The entire twisted magnetosphere above the fracture zone suddenly has nothing holding it in its stressed state. It snaps to a lower energy configuration, releasing all of that stored energy in a fraction of a second. This is why the energy released in a Magnetar flare can be so much larger than you might expect from just a crack in a crystal lattice. The crack is the trigger, but the energy comes from the magnetic field, both inside and above the star. The crust failure allows the entire magnetic system, interior field, crustal field, and magnetospheric field to suddenly rearrange, to drop from a high energy twisted state to a lower energy, less twisted state. And the difference in energy between those two states is what powers the flare. There's an analogy that might help here, and it's worth thinking through carefully because it captures the essential physics surprisingly well. Think about a dam holding back a reservoir of water. The dam is the crust. The water is the magnetic energy. As it rains, as the rivers flow, the water level behind the dam slowly rises. Day after day, the level creeps higher. The dam holds. It was built strong, engineered to withstand enormous water pressure, but the water level keeps rising. The pressure on the dam increases. Small leaks appear, thin streams of water finding their way through tiny imperfections in the structure. The engineers patch them. The water keeps rising, more leaks. The dam starts to groan. The concrete creaks under the mounting pressure. And then, one day, a section of the dam gives way. What happens next isn't just a trickle of water through a crack. It's a catastrophic release. The crack widens as the water rushes through. The force of the water tears the crack wider and wider. Adjacent sections of the dam, already stressed, fail in rapid succession. Within seconds, what started as a single crack becomes a complete structural failure, and the entire reservoir comes pouring through. The energy released has nothing to do with the strength of the concrete that broke. It has everything to do with the volume of water that was being held back. A Magnetar flare works the same way. The energy released has little to do with the mechanical energy of the cracking crust. It has everything to do with the magnetic energy that was being held in its stressed configuration by that crust. And that magnetic energy, accumulated over months or years of slow internal evolution, can be truly colossal. Now, let me address something that might seem puzzling. If the magnetic field is slowly evolving, slowly building stress, wouldn't the stress be released gradually? Wouldn't the crust just slowly deform, creeping under the magnetic pressure, releasing stress as fast as it builds? Why does it have to break suddenly and catastrophically? The answer lies in the nature of the crustal material. The crust of a neutron star is not plastic. It doesn't flow or bend gradually under sustained pressure like warm metal or soft rock. It's brittle. When stress is applied, it deforms elastically, meaning it bends slightly and stores the energy like a compressed spring. But it doesn't flow. It doesn't permanently deform. It holds its shape, storing more and more elastic energy as the stress increases. And then, when the stress exceeds a critical threshold called the yield strain, it doesn't gradually give way. It snaps. It fractures. The transition from holding to breaking is sudden, not gradual. This is the same reason glass shatters instead of bending. Glass is brittle. You can apply force to it and it will flex very slightly, storing elastic energy. But once you exceed its breaking point, it doesn't slowly bend. It shatters into pieces, releasing all the stored elastic energy at once. The crust of a neutron star behaves the same way. It's crystalline, it's rigid, it's brittle, and when it fails suddenly. Recent research using computer simulations of neutron star crusts has confirmed this picture. Simulations by groups at universities across the world, including groundbreaking work at Indiana University and at the California Institute of Technology, have modeled the response of the crustal lattice to applied magnetic stresses, using molecular dynamics techniques that track the motion of individual ions in the lattice. These simulations show that the crust behaves elastically up to a strain of about 0.1, meaning it can be deformed by about 10% from its equilibrium shape before it breaks. That might sound like a lot, but for a crystalline material, it's actually extraordinary. Most crystals on Earth, things like quartz or diamond or even high-grade structural steel, break at strains of less than 1%. The neutron star crust can withstand strains 10 times larger because of the extreme conditions under which it formed. The density, the pressure, the binding energy of the lattice. The nuclei are so tightly packed and so strongly bound that the material has an almost unbelievable capacity to resist deformation. But even a 10% strain has a limit, and when the magnetic forces push the crust beyond that limit, it fractures. The simulations show that the fracture propagates rapidly at a significant fraction of the shear wave speed in the crust, which is a substantial fraction of the speed of light. The crack doesn't creep slowly across the surface. It races across the crust, releasing energy as it goes, traveling at speeds that are a meaningful fraction of light speed itself. There's also a feedback mechanism that makes the failure self-reinforcing. When one region of the crust fractures, the stress it was bearing doesn't just disappear. It gets transferred to the surrounding crust. The neighboring regions, already strained close to their limits, suddenly have to bear additional stress. This can push them over their own breaking point, causing them to fracture as well. Their failure transfers stress to their neighbors, and so on. It's a chain reaction, a cascade of failures spreading across the crust at enormous speed. What started as a single crack in one region can propagate across a significant fraction of the star's surface in milliseconds. And as the crust fractures and shifts, the magnetic field lines that were anchored in the crust are suddenly free to move. They snap to new positions, rearranging rapidly toward a lower energy state. This rearrangement is not gentle, it's explosive. The magnetic field lines that were twisted and stressed for months or years suddenly release all their stored energy in a fraction of a second. The energy has to go somewhere. It goes into heating the material near the fracture, into accelerating charged particles to enormous energies, and into producing electromagnetic radiation. This is the birth of the flare. The trigger has been pulled. What's remarkable about this entire process is how deterministic it is. The Magnetar is not choosing when to flare. There's no randomness in the fundamental mechanism. Stress builds steadily, driven by well-understood physical processes in the interior. The crust resists until it can't resist anymore. The failure point is determined by the breaking strain of the material and the rate at which stress accumulates. In principle, if you knew the exact state of the magnetic field throughout the star and the exact properties of the crust at every point, you could predict when and where the next flare would occur. In practice, we can't do this because we don't have that detailed knowledge. We can't see inside a magnetar. We can't map its internal field. So the flares appear to us as unpredictable, sudden, violent. But they're not random. They're the inevitable consequence of physics operating under extreme conditions. The magnetic field evolves. The crust strains. The strain reaches its limit. And then, in a fraction of a second, everything changes. We're now at the moment of rupture. The crust has been holding for months or years, bearing stresses that would destroy any other material in the universe. The magnetic field in the interior has been slowly, relentlessly twisting, loading more and more energy into the crust and the magnetosphere above it. Small cracks have appeared. Small bursts have been released. The activity has been escalating. And now, in one critical region where the stress is highest and the field geometry is most complex, the crust reaches its breaking strain. The strongest material in the known universe is about to fail. What happens next will unfold in less than a second. But in that fraction of a second, more energy will be released than our sun produces in 250,000 years. The flare is about to begin. The crust breaks. After months or years of accumulating stress, after countless small fractures and minor bursts that signaled the growing instability, the strongest material in the known universe finally reaches its limit. Somewhere on the surface of this spinning dead star, in a region where the magnetic field geometry is most twisted and the stress is most concentrated, the crystalline lattice of neutron-rich nuclei tears apart. The fracture doesn't start slowly. It doesn't creep or ease, open gradually. It initiates at a point and then races outward across the crust at a velocity that is a significant fraction of the speed of light. The sheer wave speed in neutron star crust material is roughly 1/10 to 1/3 of the speed of light. Somewhere between 30,000 and 100,000 kilometers per second. The crack propagates at a speed comparable to this, which means it can cross a significant portion of the star's surface, several kilometers, in less than a millisecond, less than 1,000th of a second. In the time it takes a hummingbird's wing to complete a single stroke, the fracture has already torn across a region of crust larger than a mountain range, and the fracture doesn't stay small. That cascading failure doesn't stay confined to one small patch. In the case of a giant flare, it sweeps across a substantial fraction of the magnetar's entire crust. Not all of it necessarily, but a large enough section that the magnetic field configuration is fundamentally and irreversibly altered across a significant portion of the star. The sound of it, if sound could travel through the vacuum of space, would be a roar beyond anything the human ear could process. A vibration at frequencies that would shake apart any solid object within range. Imagine an earthquake so large that it doesn't just rupture one fault line. It ruptures every fault line on an entire continent simultaneously, all within the span of a heartbeat, releasing the accumulated stress of centuries in one cataclysmic moment. That's the scale of what happens during a Magnetar giant flare, except compressed into a volume 12 miles across and unfolding in a fraction of a second. And unlike an earthquake on Earth, where the energy dissipates into seismic waves that gradually fade, the energy released in a Magnetar crust failure doesn't just rumble and die out. It feeds directly into the magnetic field above, igniting a chain of events that will convert that mechanical rupture into something far more powerful, a magnetic detonation that dwarfs the cracking itself by orders of magnitude. Now, the cracking of the crust is dramatic, but it's not the main event. The crust failure is the trigger, not the explosion. What happens next is where the truly staggering energy release occurs, and it involves the magnetic field. Remember, the magnetic field lines of the Magnetar are anchored in the crust. They thread through the crystalline lattice, locked in place by the rigidity of the material. Above the surface, these field lines arch up into the magnetosphere, looping through space in complex, twisted configurations that have been slowly wound up over months or years of internal magnetic evolution. These twisted magnetospheric field lines store enormous amounts of energy that has been building as the internal processes twisted the field at its base, and the crust held those twisted configurations in place. When the crust fractures and shifts, those anchor points suddenly move. The base of the magnetic field lines is displaced. Field lines that were held in stressed, twisted configurations by the rigid crust are suddenly free to rearrange. And they do rearrange, violently and almost instantaneously. The process that occurs is analogous to what solar physicists call magnetic reconnection, but it happens under conditions far more extreme than anything observed on the Sun. Let me explain what magnetic reconnection is, because it's absolutely central to understanding how the flare produces its energy. Magnetic field lines have a property that in most circumstances they don't like to cross each other. They resist being pushed together. Two field lines running in the same direction will happily sit side by side, but two field lines running in opposite directions create a problem. They push against each other, building up magnetic pressure in the region between them, creating a kind of standoff where neither set of lines can advance. But if the conditions are right, if the field lines are pushed together hard enough and fast enough, if the region between them becomes thin enough and hot enough, something remarkable happens. The field lines break and reconnect in a new configuration. The topology of the field changes instantaneously. Lines that were running in one direction connect to lines that were running in another direction, forming new loops or new open configurations that have less total energy than the original stressed arrangement. The difference in energy, the energy that the field had in its stressed state, minus the energy it has in its new relaxed state, has to go somewhere. It goes into heating and accelerating the local plasma. This reconnection converts magnetic energy into other forms of energy, primarily kinetic energy of particles and thermal energy, with extraordinary efficiency. In some theoretical models, magnetic reconnection can convert up to 50% of the stored magnetic energy into particle energy and radiation. It is one of the most efficient energy conversion mechanisms in all of astrophysics. On the Sun, magnetic reconnection powers solar flares. The Sun's magnetic field gets twisted and tangled by the motion of plasma in its outer layers. When the field becomes too stressed, reconnection occurs, and the stored magnetic energy is released as a burst of radiation and energetic particles. A large solar flare releases about 10 to the 32 e-ergs of energy. That's enough to disrupt radio communications on Earth, trigger geomagnetic storms, and create beautiful auroras. Solar flares are considered among the most energetic events in our solar system. A Magnetar giant flare releases roughly 10 to the 44 to 10 to the 46 ergs. That is 1 trillion to 100 trillion times more energy than the most powerful solar flare. The physics is similar in principle. Magnetic stress builds, reconnection occurs, energy is released, but the scale is incomprehensibly different. It's like comparing a firecracker to a thermonuclear weapon. Both involve rapid energy release, but the magnitude is so different that they're essentially different phenomena. On a magnetar, the reconnection happens in a magnetic field that is 1 quadrillion times stronger than the sun's surface field. The energy density in the magnetar's magnetosphere is correspondingly higher, and the reconnection, triggered by the sudden displacement of field line anchor points when the crust fractures, proceeds with explosive speed. The field doesn't gently rearrange itself over hours or days, as it sometimes does on the sun. It snaps from one configuration to another in milliseconds. The entire twisted magnetosphere above the fracture zone collapses into a simpler, lower energy state in less time than it takes you to blink. Here is where the physics becomes particularly fascinating and particularly extreme. When the magnetic field reconnects and releases its stored energy, that energy has to go somewhere. On the sun, reconnection energy goes primarily into heating solar plasma and accelerating particles. On a magnetar, the energy goes into creating something far more exotic, far more extreme than anything the sun could ever produce. The energy density in the reconnection region is so high that it creates what physicists call a pair fireball, an incredibly hot cloud of electrons, positrons, and gamma-ray photons. Let me explain how this works. When the magnetic field reconnects and dumps its energy into the local environment, the temperature in the reconnection zone rises to extraordinary levels. We're talking about temperatures of billions of degrees, possibly tens of billions of degrees. At these temperatures, the photons, the particles of light, have enough energy to spontaneously convert into matter. Specifically, they have enough energy to create electron-positron pairs. A positron is the antimatter counterpart of an electron. It has the same mass as an electron, but opposite electric charge. When a photon has enough energy, it can split into an electron and a positron. This process is called pair production, and it's a direct consequence of Einstein's famous equation relating energy and mass. Energy can become matter, and matter can become energy. In the reconnection zone of a magnetar flare, pair production happens on a massive scale. The gamma-ray photons created by the reconnection are so energetic that they constantly produce electron-positron pairs. These aren't occasional events. The pair production rate is astronomical, creating vast numbers of particles every microsecond. But those pairs immediately annihilate each other, colliding and converting back into gamma-ray photons. And those photons, still energetic enough, produce more pairs. And those pairs annihilate to produce more photons. It's a cycle, a furious equilibrium of creation and destruction happening trillions upon trillions of times per second. The result is a self-sustaining fireball of electrons, positrons, and gamma rays, all in approximate thermal equilibrium, all at a temperature of billions of degrees. This is not ordinary matter in any sense. There are no atoms here, no molecules, no chemistry. Just a seething cloud of the most fundamental particles and the most energetic photons, creating and destroying each other endlessly. This fireball is optically thick, meaning photons can't easily escape from it. They keep getting absorbed and re-emitted, interacting with the electron-positron pairs, bouncing around inside the fireball like light trapped in a fog. The fireball is essentially a blob of almost pure energy, trapped temporarily by its own opacity, glowing at temperatures that exceed the cores of the most massive stars. And this fireball is confined by the magnetic field. Even though the field has reconnected and simplified, it's still extraordinarily strong. The remaining magnetic field lines loop over the fracture zone, forming a kind of magnetic bottle that contains the fireball, preventing it from expanding freely into space. The fireball sits on the surface of the Magnetar, trapped in a magnetic cage, pulsating and radiating. Think of it as a bubble of pure energy, hotter than the core of most stars, trapped on the surface of a dead star by magnetic forces that exceed anything else in the known universe. This is the fundamental structure of a Magnetar flare, a pair fireball created by magnetic reconnection, confined by the remaining magnetic field, sitting on or near the surface of the neutron star. The fireball radiates energy as gamma rays and hard X-rays. Some of this radiation escapes directly from the fireball's surface. Some escapes through gaps in the magnetic confinement, and the fireball gradually cools and shrinks as it radiates its energy away. This process produces the observed emission that our telescopes detect from thousands of light years away. Now, this is where we need to draw a critical distinction, because not all Magnetar flares are the same. There's a spectrum of events, ranging from relatively modest bursts to the rare, catastrophic giant flares, and the difference between them is not just a matter of how much energy is released. The physics is qualitatively different. At the lower end of the spectrum are ordinary Magnetar bursts. These are produced when a small localized region of crust fractures, maybe a patch a few hundred meters across, shifts slightly, allowing a limited amount of magnetic reconnection in the magnetosphere directly above. The resulting fireball is small and doesn't last long. It produces a brief pulse of hard X-rays lasting a fraction of a second, with a total energy release of perhaps 10 to the 38 to 10 to the 41 ergs. These bursts are relatively common among active magnetars. Active magnetars can produce dozens or even hundreds of these small bursts over a period of weeks during an active episode. Each one represents a small, localized stress release, a tiny earthquake on the Magnetar surface. They're energetic by any terrestrial standard, each one releasing more energy than the sun produces in a full second. But by Magnetar standards, they're modest. They don't fundamentally alter the magnetic field configuration. They're local events that relieve stress in one small region without affecting the rest of the star significantly. In the middle of the spectrum are intermediate flares. These involve larger fracture zones and more extensive magnetic reconnection. They release energies of around 10 to the 41 to 10 to the 43 ergs and can last for several seconds. They're less common than ordinary bursts, but more common than giant flares. They represent significant stress releases that involve a meaningful area of the crust and a substantial volume of the magnetosphere. They can produce noticeable and lasting changes in the magnetar's behavior, altering its spin rate, slightly or changing the character of its persistent X-ray emission for days or weeks afterward. And then, at the extreme end, there are the giant flares. These are the events we've been building toward this entire time. Giant flares are extraordinarily rare. In the roughly 50 years that we've had the ability to detect them, we've observed only 3 confirmed giant flares from magnetars in or near our galaxy. Just 3 events in half a century of observation. They occur when the cascading crust failure involves a very large fraction of the star's surface, when the magnetic field rearrangement is not localized, but global, involving a fundamental restructuring of the entire magnetospheric field configuration. The energy released in a giant flare is on the order of 10 to the 44 to 10 to the 46 ergs. The most powerful of the 3 observed giant flares released roughly 3 times 10 to the 46 ergs. That is approximately the amount of energy our sun produces in 250,000 years, released in less than 1/5 of a second. Let me say that again because the numbers are important. 250,000 years of solar energy output, compressed into a burst lasting less than 2/10 of a second. The peak luminosity during that initial spike exceeds 10 to the 47 ergs per second. For that brief instant, the Magnetar is more luminous than an entire galaxy. Not a small galaxy. A large spiral galaxy like the Milky Way, containing hundreds of billions of stars. For a fraction of a second, one dead star 12 miles across outshines all of them combined. The structure of a giant flare is distinctive, and it tells us a great deal about the physics of the event. The emission has 2 phases, and understanding both is crucial to understanding what's actually happening on the star. The first phase is the initial spike. This is a brief, extraordinarily intense burst of hard gamma rays lasting between 1/10 and 1/2 of a second. This spike contains most of the total energy of the flare, often 90% or more. The spike corresponds to the moment of crust failure and the immediate explosive magnetic reconnection that follows. Everything happened so fast that the entire energy budget of the flare, energy equivalent to hundreds of thousands of years of solar luminosity, is crammed into a window of time shorter than a single human heartbeat. The energy released during the spike is so intense that it overwhelms the detectors on most gamma-ray satellites. The instruments literally saturate. They can't measure the true brightness because it's beyond their designed range. The electronics were never built to handle signals this powerful arriving this suddenly. This has made it challenging to determine the exact peak luminosity of giant flares, because during the most critical moments, our instruments are essentially blinded by the intensity of the event. Reconstructing what actually happened during the spike requires careful analysis of the saturated data, looking at the edges of the signal, the way the detectors recovered, and using instruments that happen to be pointed slightly away from the source and caught only a fraction of the irradiation. During the initial spike, the pair fireball is created and expands rapidly within its magnetic confinement. The fireball expands outward from the fracture zone at a speed that is a significant fraction of the speed of light. Within milliseconds, it can engulf a substantial portion of the Magnetar's magnetosphere. The energy in the fireball is so great and the expansion so violent that it can actually deform the magnetic field that's trying to contain it. The fireball and the magnetic field are locked in a dynamic struggle. The magnetic field tries to contain the fireball, but the fireball's internal pressure pushes back against the field. In regions where the fireball pressure exceeds the magnetic pressure, the fireball breaks through and plasma escapes into space. In regions where the magnetic field is strong enough, it holds and the fireball remains trapped. The second phase of the giant flare is the oscillating tail. After the initial spike, the emission doesn't simply stop. Instead, it transitions into a lower intensity but longer lasting tail that can persist for several minutes. This tail has a remarkable property. It pulsates, oscillating in brightness with a period that exactly matches the rotation period of the magnetar. As the magnetar spins, the region where the fireball is trapped rotates in and out of our line of sight, causing the observed brightness to rise and fall with each rotation. This is direct evidence that the fireball is confined to a specific region on the star's surface, rather than being distributed uniformly. If the fireball was spread evenly around the entire star, there would be no pulsation. The fact that we see pulsations tells us the fireball is localized, sitting on one part of the star and rotating with it as the star spins. But the oscillating tail reveals something even more extraordinary. Superimposed on the rotational pulsations are higher frequency oscillations, rapid fluctuations in brightness with periods of tens to hundreds of milliseconds. These oscillations were first detected in the tail of the giant flare of December 27, 2004, and they caused enormous excitement in the astrophysics community. Because these oscillations are believed to be the seismic vibrations of the neutron star itself, when the crust fractures during the giant flare, it doesn't just crack, it rings. The entire star vibrates, oscillating in modes analogous to the way a bell vibrates after being struck, or the way Earth's surface oscillates after a major earthquake. Seismologists on Earth study earthquake vibrations to learn about the planet's interior structure, the composition and density of the mantle and core. In exactly the same way, the vibrations detected in the tails of Magnetar giant flares carry information about the interior structure of the neutron star. The frequencies of the oscillations depend on the star's density, its size, the composition of its crust, and the properties of the superfluid interior. By measuring these frequencies and comparing them to theoretical models, astronomers can constrain the equation of state of matter at nuclear density, one of the most fundamental unsolved problems in physics. This field is called asterosismology when applied to ordinary stars, and neutron star seismology when applied to neutron stars. The detection of seismic oscillations in Magnetar giant flare tails opened an entirely new window into the physics of ultra-dense matter. It was the first time we could probe the interior of a neutron star through its vibrations, just as geologists probe the interior of the Earth through seismic waves. The frequencies detected in the 2004 flare ranged from about 18 Hz to over 1000 Hz. Different frequencies correspond to different oscillation modes. The lowest frequency modes involve large-scale deformations of the entire star. Higher frequency modes involve smaller-scale vibrations of the crust. Each mode is sensitive to different aspects of the star's internal structure. By measuring multiple modes, astronomers can build up a detailed picture of the neutron star's interior, constraining the density profile, the thickness of the crust, and the properties of the superfluid core. The fireball trapped on the magnetar's surface gradually cools and shrinks over the minutes following the initial spike. As it cools, the electron-positron pairs annihilate and are no longer replenished because the temperature has dropped below the threshold for pair production. the fireball transitions from a pair-dominated plasma to a photon-dominated plasma, and eventually the remaining energy radiates away. The magnetic field that was confining the fireball gradually returns to a more stable configuration, though not the same configuration it had before the flare. The flare has permanently altered the magnetic field structure. The field has relaxed to a lower energy state, releasing some of its stored energy in the process. But it's still enormously powerful, still a magnetostrength field. The stress has been partially relieved, not completely eliminated. The crust has shifted to a new position. The magnetic field has found a new equilibrium. And the slow process of stress accumulation begins again. There's another phenomenon that occurs during giant flares that deserves attention because it illustrates just how extreme these events truly are. During the most powerful giant flares, the energy released is so enormous that it ejects matter from the Magnetar surface. The intense radiation pressure and the magnetic forces can launch clouds of plasma into space at relativistic speeds, meaning speeds that are a significant fraction of the speed of light. These ejected clouds have been observed as expanding radio nebulae in the weeks and months following giant flares. After the December 27th, 2004 giant flare from SGR 1806-20, radio telescopes detected an expanding cloud of debris moving outward from the Magnetar at roughly 1/3 the speed of light. 1/3 of the speed of light. That's approximately 100,000 kilometers per second. Material ejected from a star 12 miles across, accelerated to speeds that would carry it from Earth to the Moon in less than 4 seconds. This ejected material was likely a combination of crustal matter torn loose during the fracture and magnetospheric plasma accelerated by the flare. The cloud expanded and faded over the following weeks as it interacted with the surrounding interstellar medium, producing radio emission that could be tracked by telescopes on Earth. The total mass ejected during a giant flare is relatively small, perhaps equivalent to a small asteroid's worth of material. But the speed at which it's moving and the energy it carries are remarkable. This ejected material is one of the ways a magnetar permanently loses energy during a flare. The energy goes into radiation, into seismic vibrations of the star, into heating the crust and interior, and into ejecting this high-speed debris. Each giant flare leaves the magnetar slightly less energetic than before, its magnetic field slightly weaker, its crust shifted into a new configuration. The 3 confirmed giant flares we have observed occurred on March 5th, 1979, August 27th, 1998, and December 27th, 2004. 3 events in nearly 50 years. That's how rare these are. Each one was detected by gamma-ray satellites orbiting Earth, instruments designed primarily to study gamma-ray bursts from distant galaxies, not to observe events within our own Milky Way. When these flares went off, they were so bright that they overwhelmed the detectors, blinding the instruments and saturating the electronics. The flares arrived without warning, announced by nothing more than a sudden, overwhelming flood of gamma-ray photons that lit up every detector pointed in their general direction. In each case, the initial reaction was confusion. The signals didn't match any known type of gamma-ray burst. They were too bright, too sharp, too short in their initial spike, and their oscillating tails were unlike anything seen from cosmological gamma-ray bursts. It took careful analysis, weeks and months of work by teams of scientists around the world to determine that these weren't explosions in distant galaxies, but something much closer to home. Something happening on magnetars within our own galaxy or in nearby satellite galaxies. Something fundamentally different from anything that had been observed before. The December 2004 event was particularly dramatic because it was by far the most energetic of the three. It was so powerful that it measurably affected Earth's ionosphere from a distance of roughly 50,000 light years. The gamma rays from this event, traveling for 50,000 years across the galaxy at the speed of light, were still intense enough when they arrived at Earth to ionize atoms in our upper atmosphere and compress the boundary of Earth's magnetic field. A dead star on the other side of the galaxy, an object 12 miles across that exploded for less than a second, physically altered the atmosphere of our planet 50,000 years later. That's how powerful a Magnetar giant flare is. The crust has cracked. The magnetic field has reconnected. The fireball has formed and is radiating its energy into space. The star is ringing like a bell, its seismic vibrations carrying information about the densest matter in the universe. Debris is flying outward at a third the speed of light. And the gamma rays, the messengers of this cataclysm, are racing outward in all directions at the speed of light, carrying the news of the flare to any detector fortunate or unfortunate enough to be in their path. What happens when those gamma rays reach the rest of the universe, and what they tell us about physics at the most extreme limits, is what we need to explore next. The gamma rays are now traveling through space at the speed of light. They left the surface of a magnetar, a dead star 12 miles across, somewhere in our galaxy, and they're radiating outward in all directions. They carry with them the signature of one of the most violent events the universe can produce. A burst of electromagnetic radiation so intense that for a fraction of a second, this single star outshone an entire galaxy. And these gamma rays don't care what's in their path. They don't slow down. They don't lose energy over short distances. They travel at 300,000 kilometers per second, the fastest speed anything in the universe can move, and they will keep going until something absorbs them. If a planet happens to be in the way, the gamma rays will hit it. And what happens next depends entirely on how far away that planet is. Let's start with what happened to Earth, because we don't have to speculate about this. It actually occurred. On December 27th, 2004, a giant flare from the Magnetar designated SGR 1806-20 reached our planet. This Magnetar sits roughly 50,000 light years from Earth, on the far side of the Milky Way galaxy. The flare itself had occurred 50,000 years earlier, back when modern humans shared Europe with Neanderthals, when the last ice age was approaching its peak, and most of northern Europe was buried under kilometers of glacial ice. The gamma rays had been traveling through space for all of that time, crossing the entire breadth of the galaxy, passing countless stars and planetary systems along the way. And on December 27th, 2004, they arrived at Earth. The initial spike of the flare lasted about 0.2 of a second. In that brief window, the flux of gamma rays hitting the upper atmosphere was enormous. Despite having traveled 50,000 light years, despite having spread out over a sphere with a surface area of roughly 3 × 10 to the 43 square centimeters, the radiation was still intense enough to have measurable physical effects on our planet. The gamma rays ionized atoms in the upper atmosphere, temporarily increasing the electron density in the ionosphere by a factor of several. This is the same layer of the atmosphere that reflects radio waves and enables long-distance radio communication. The sudden increase in ionization disrupted radio signals and was detected by instruments monitoring the ionosphere. It was nighttime over the Americas when the flare arrived, and the effects were measured by receivers that track very low frequency radio signals bouncing off the ionosphere. The data showed a clear, sudden disturbance at the exact moment the gamma rays arrived. A disturbance that shouldn't have been there, that had no explanation in terms of solar activity or terrestrial weather. It was caused by a dead star on the other side of the galaxy. The flare also temporarily compressed Earth's magnetosphere. The magnetosphere is the bubble of magnetic influence surrounding our planet, shaped by the interaction between Earth's magnetic field and the solar wind. It normally extends tens of thousands of kilometers into space on the side facing the sun. When the gamma ray pulse from the Magnetar hit, the intense radiation briefly increased the ionization and conductivity of the upper magnetosphere, causing it to contract slightly. The effect was small and temporary, lasting only seconds. But it was real, and it was measurable. A star 50,000 light-years away, an object so distant that its light takes 50 millennia to reach us, physically deformed the magnetic shield of our planet for a few seconds. Think about the power required to do that across such a distance. The gamma rays had spread out over a sphere 50,000 light-years in radius, and yet the tiny fraction of them that intercepted Earth, a fraction so small it's almost zero, was still enough to alter the ionosphere and push on the magnetosphere. Now, Earth was 50,000 light-years away from this particular Magnetar. That's an enormous distance. It's halfway across the galaxy. The effects on Earth were measurable, but not dangerous. They were scientific curiosities, data points for researchers to analyze. Nobody on the ground noticed anything. No one got sick. No electronics were damaged. The ozone layer wasn't affected. Life went on as normal. The flare was a spectacular event for astronomers, but it was harmless to people on the surface. But what if the Magnetar had been closer? This is where things become genuinely unsettling. Because magnetars are not all conveniently located on the far side of the galaxy. Some are much closer. And the intensity of radiation follows an inverse square law. If you halve the distance, you quadruple the intensity. If you reduce the distance by a factor of 10, the intensity increases by a factor of 100. If you reduce the distance by a factor of 1,000, the intensity increases by a factor of 1,000,000. The December 2004 flare came from 50,000 light-years away. If the same flare had come from a Magnetar 50 light-years away, which is still a vast distance by human standards but well within our stellar neighborhood, the radiation intensity at Earth would have been 1,000,000 times greater. 1,000,000 times. That's not a typo, and it's not an exaggeration. It's a straightforward consequence of the inverse square law. 50,000 divided by 50 is 1,000, and 1,000 squared is 1,000,000. The gamma ray flux would be 1,000,000 times what we experienced in 2004. At that intensity, the consequences for life on this planet would be catastrophic. At that intensity, the gamma rays would strip a significant fraction of the ozone layer. The ozone layer, that thin shell of molecules in the stratosphere that absorbs ultraviolet radiation from the sun, is the only thing protecting life on Earth's surface from being sterilized by solar ultraviolet light. Without it, UV radiation reaching the ground would increase dramatically, damaging DNA in every organism exposed to sunlight. Plants would be harmed. Phytoplankton in the ocean, the tiny organisms that produce a substantial fraction of Earth's oxygen and form the base of the marine food chain, would be killed in large numbers. The effects would cascade up through ecosystems. Animals that depend on plants would starve. Predators that depend on those animals would starve. Within months or years, entire food webs could collapse, and the ozone wouldn't recover immediately. Depending on how severely it was damaged, full recovery could take years or even decades. During that time, elevated UV radiation would continue to stress every ecosystem on the planet. At even closer distances, say 10 light years, the effects would be dramatically worse. The radiation intensity would be 25 billion times what Earth experienced in 2004. At that level, the gamma rays wouldn't just damage the ozone layer, they would destroy it almost entirely. The burst of ionizing radiation hitting the atmosphere would also produce enormous quantities of nitrogen oxides, reactive chemicals that further attack ozone and can persist in the stratosphere for years. The resulting UV increase at the surface would be severe enough to cause widespread cell damage in exposed organisms, skin cancers in animals, blindness from UV damage to eyes, destruction of plant tissue, mass die-offs in marine ecosystems as phytoplankton are killed faster than they can reproduce. The effects would resemble a mass extinction event, potentially comparable to some of the great extinctions in Earth's geological past. Could a Magnetar flare actually cause a mass extinction? Some scientists have speculated about this. The fossil record shows 5 major mass extinction events over the past 500 million years, along with dozens of smaller extinction events. The causes of some of these events are well understood. The extinction that killed the dinosaurs 66 million years ago was caused by an asteroid impact. But the causes of other extinctions are less clear. The largest mass extinction of all, the Permian-Triassic extinction roughly 252 million years ago, killed approximately 90 to 96% of all marine species and roughly 70% of terrestrial vertebrate species. The cause is debated, with massive volcanic eruptions in what is now Siberia being the leading candidate, but some researchers have proposed that a nearby gamma-ray event, whether from a Magnetar flare or from a related phenomenon called a short gamma-ray burst, could have contributed to past mass extinctions. The hypothesis is difficult to test because a gamma-ray event wouldn't leave an obvious physical signature in the geological record the way an asteroid impact does. An asteroid leaves behind a layer of iridium-rich dust and shocked quartz. A gamma-ray event leaves behind only the indirect effects of ozone destruction, increased UV radiation, and ecological collapse. These effects could be caused by many things, and are hard to attribute uniquely to a gamma-ray source. So, while the idea remains speculative, it's not dismissed by the scientific community. It's considered a plausible, if unproven, mechanism for at least some of the smaller extinction events in Earth's history. The good news is that there are no known magnetars close enough to Earth to pose an immediate threat. The nearest known magnetar is several thousand light years away. At that distance, even a giant flare would produce effects comparable to or smaller than what we experienced in 2004. Noticeable to instruments, but harmless to life. However, our census of magnetars is far from complete. We've identified fewer than 30 magnetars in the Milky Way, but there are estimated to be several thousand in the galaxy. Most are hidden from us, too faint or too far away to detect during their quiet periods. We find them primarily when they flare, which means there could be magnetars much closer to Earth that we simply haven't identified yet, because they haven't produced a detectable outburst during the few decades we've been watching. There's another dimension to the aftermath of a magnetar flare that extends far beyond its effects on any particular planet. Giant flares are so bright that they can be detected from enormous distances, not just within our galaxy, but from other galaxies entirely. And this has created an interesting problem in astronomy that took years to untangle. When gamma-ray satellites first began operating in the 1960s and 70s, they detected mysterious bursts of gamma rays coming from random directions in the sky. These gamma-ray bursts were completely unpredicted by theory. No one knew what caused them. For decades, astronomers debated whether they came from nearby sources within our galaxy or from incredibly distant sources in other galaxies. The debate was eventually settled in the late 1990s when it was shown that most gamma-ray bursts come from cosmological distances, billions of light years away. These cosmological gamma-ray bursts are produced by the deaths of massive stars or the mergers of neutron stars, and they are the most energetic explosions in the universe since the Big Bang. But there was a category of shorter, less energetic bursts that didn't fit neatly into this picture. Some gamma-ray bursts lasted only a fraction of a second and came from directions that coincided with nearby galaxies. Galaxies within a few tens of millions of light years. Were these the same type of event as the cosmological bursts? Just smaller versions? Or were they something entirely different? It's now understood that at least some of these short bursts from nearby galaxies are magnetar giant flares. A giant flare occurring in a galaxy 10 or 20 million light years away would appear to our detectors as a short, intense burst of gamma rays. It would look very similar to certain types of cosmological gamma ray bursts, and without careful analysis, it could easily be misidentified. This realization came gradually as astronomers studied the properties of these bursts in detail and noticed that some of them had characteristics, energy spectra, time profiles, and locations within their host galaxies that were more consistent with magnetar flares than with the standard models of gamma-ray bursts. This has significant implications for astronomy. If some of the short gamma-ray bursts we've detected over the years are actually magnetar giant flares in distant galaxies rather than neutron star mergers or other cosmological events, then our catalogues of gamma-ray bursts need to be revised. The statistics change. The rates of different types of events change. Our understanding of how often neutron star mergers occur, which has implications for gravitational wave astronomy and for the production of heavy elements like gold and platinum, could be affected by how many events we've been misclassifying. Astronomers are actively working on this problem right now, trying to determine which short gamma-ray bursts in the existing catalogues are genuine cosmological events and which might be extragalactic magnetar flares masquerading as something else. The ability to detect magnetar flares from other galaxies also opens up a new way to study magnetars themselves. Within our galaxy, we can only observe the magnetars that happen to be active during the few decades we've had gamma-ray satellites in orbit. But by looking at other galaxies, we can survey much larger populations of stars and potentially catch giant flares that are very rare. Events that might happen only once every few decades or centuries in any given galaxy. By monitoring many galaxies simultaneously, we increase our chances of catching a giant flare in progress and studying it with our full suite of instruments. This is exactly what astronomers are doing, using gamma-ray satellites to watch for sudden bright flashes from the directions of nearby galaxies, hoping to catch the next giant flare and study it with more sophisticated instruments than were available for the 3 events we've already observed. Let's talk about what magnetar flares teach us about fundamental physics, because this is perhaps the most profound aspect of the entire subject. Magnetars are laboratories for physics that we cannot reproduce on Earth. The conditions inside and around a magnetar, the density, the magnetic field strength, the gravitational field, are so extreme that they test our theories of physics in regimes that no laboratory experiment can access. Every magnetar flare that we observe provides data that constrains our understanding of matter, energy, and the fundamental forces of nature. The equation of state of dense matter, the relationship between pressure and density at nuclear and supranuclear densities, is one of the biggest open questions in physics. We know how matter behaves at the densities we can achieve in laboratory experiments. We know how it behaves at everyday densities, but we don't know exactly how it behaves when you compress it to the density of an atomic nucleus and beyond. Does it stiffen, becoming harder to compress? Does it soften? Does it undergo phase transitions, changing from one form of matter to another? Perhaps from ordinary nuclear matter to quark matter? The answers to these questions determine the maximum mass a neutron star can have, its radius, its internal structure, and how it vibrates when disturbed. Magnetar flares provide a unique window into these questions. These seismic oscillations detected in giant flare tails are directly sensitive to the equation of state. Different equations of state predict different oscillation frequencies. By measuring the frequencies and comparing them to theoretical predictions, we can constrain which equations of state are consistent with the reality and which are not. The oscillations detected in the December 2004 flare have already ruled out some theoretical models and supported others. Future observations of giant flare oscillations with more sensitive instruments could provide even tighter constraints, potentially resolving questions that have been debated for decades. Magnetar flares also test our understanding of quantum electrodynamics in strong magnetic fields. Quantum electrodynamics, or QED, is the theory that describes how light and charged particles interact. It's one of the most precisely tested theories in all of physics. In laboratory conditions, QED predictions match experimental measurements to extraordinary precision, often to 10 or more decimal places. But all of those laboratory tests have been conducted in relatively weak magnetic fields. Fields millions of times weaker than a magnetar's. In the ultra-strong fields of a magnetar, QED predicts exotic effects. Vacuum birefringence, where empty space splits light into 2 polarizations. Photon splitting, where a single photon spontaneously divides into 2 lower energy photons. Magnetic pair production, where the magnetic field itself converts photon energy into electron-positron pairs. These effects are predicted by QED, but have never been directly observed in a laboratory because we can't create magnetic fields strong enough. Magnetars are the only places in the universe where these effects occur naturally, and magnetar flares, with their intense radiation passing through ultra-strong fields, provide the best opportunity to observe them. Observations of the polarization of X-rays from magnetars, currently being conducted by instruments like the Imaging X-ray Polarimetry Explorer satellite, launched in 2021, are beginning to test these predictions. Early results are consistent with vacuum birefringence, supporting QED's predictions in the strong field regime. But more observations are needed, and future Magnetar flares will provide invaluable data. Magnetars also teach us about the behavior of matter in the strongest gravitational fields short of a black hole. The surface gravity of a magnetar is about 200 billion times Earth's. Light emitted from the surface is significantly redshifted by the gravitational field, meaning its wavelength is stretched and its energy reduced as it climbs out of the gravitational well. By measuring this gravitational redshift in the spectra of Magnetar flares, astronomers can determine the ratio of the star's mass to its radius, constraining the equation of state from yet another angle. The gravitational field also bends light, causing gravitational lensing effects that allow us to see slightly around the curve of the star. This means that during a Magnetar flare, we can observe radiation from surface areas slightly larger than the hemisphere facing us. These effects are measurable and provide additional information about the star's size and mass. Let's zoom out and think about what magnetars mean for the broader story of the universe. Magnetars are born from the deaths of massive stars. The same supernovae that create magnetars also create and disperse heavy elements into the interstellar medium. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was forged in stars and dispersed by supernovae. Some of those supernovae created magnetars. So magnetars are intimately connected to the chemical enrichment of the universe, the process that made rocky planets and complex chemistry and ultimately life possible. Magnetars are also connected to some of the most mysterious phenomena in modern astronomy. In 2007, astronomers discovered a new type of radio signal called a fast radio burst. These are extremely brief, extremely bright pulses of radio waves coming from distant galaxies. Each burst lasts only a few milliseconds, but during that time it releases as much energy and radio waves as the sun produces in days or weeks. The origin of fast radio bursts was one of the biggest mysteries in astronomy for over a decade. Dozens of theories were proposed, ranging from neutron star collisions to alien technology. Then, in April 2020, a magnetar in our own galaxy, SGR 1935 plus 2154, produced a burst of radio waves that looked exactly like a fast radio burst, accompanied by a simultaneous burst of X-rays characteristic of magnetar activity. This was the smoking gun. It provided strong evidence that at least some fast radio bursts are produced by magnetars, likely during flare events, where the magnetic field rearrangement accelerates particles that emit coherent radio emission. This discovery connected two previously separate fields of astronomy, magnetar physics, and fast radio burst research, and opened new avenues for studying both. As we reach the end of this journey, I want you to think about what we've covered tonight. We started with a dead star, the collapsed core of a massive sun that exploded long ago. We learned that this remnant, a neutron star, is compressed to densities beyond anything in everyday experience. Matter crushed to the point where atoms cease to exist, and only neutrons remain, packed together at nuclear density in a sphere 12 miles across. We learned that some of these neutron stars are born with magnetic fields so powerful they distort the vacuum of empty space fields a quadrillion times stronger than Earth's. These are magnetars, and they are among the most extreme objects in the known universe. We trace the slow buildup of magnetic stress inside a magnetar. We saw how the superfluid interior evolves, pushing on the rigid crust from below, loading it with forces that even the strongest material in existence can barely withstand. We understood why this stress accumulates rather than being released gradually, because the crust is brittle, holding elastically until it suddenly and catastrophically fails. We witness the moment of failure. The crust cracks. The fracture cascades across the star's surface in milliseconds. The magnetic field, freed from its rigid anchor, snaps into a new configuration through explosive reconnection. A fireball of electrons, positrons, and gamma rays erupts on the surface, confined by the remaining magnetic field, radiating energy at a rate that briefly exceeds the luminosity of an entire galaxy. And we followed the gamma rays outward, across the galaxy and beyond. We saw how they affected Earth's atmosphere from 50,000 light-years away. We considered what would happen if a magnetar were closer, how a giant flare could strip the ozone layer and trigger ecological catastrophe. We explored how magnetar flares masquerade as gamma-ray bursts from other galaxies, confusing our astronomical catalogues. And we discussed how magnetars serve as laboratories for fundamental physics, testing our theories of matter, light, and gravity under conditions no experiment on Earth can replicate. There's something humbling about all of this. We live our lives on a planet that feels solid and permanent. The ground beneath our feet seems stable. The sky above seems calm. But out there, scattered across the galaxy, are objects so extreme that they challenge our ability to comprehend them. Stars where a teaspoon of material weighs 4 billion tons. Magnetic fields that warp the fabric of empty space. Explosions that release more energy in 1/10 of a second than our sun produces in 250,000 years. And all of it is happening right now, somewhere in the Milky Way. There are magnetars in our galaxy building stress in their crusts at this very moment. The internal magnetic fields are slowly twisting. The crusts are slowly straining. Small bursts are being released. And eventually, without warning, one of them will produce a giant flare. We don't know when. We don't know which magnetar. We don't know in which direction the brightest part of the flare will be aimed. But we know it will happen because the physics demands it. Magnetic stress builds, crusts break, fields reconnect, fireballs form, gamma rays fly. It's inevitable, written into the equations that govern the behavior of matter and energy at their most extreme. And when the next giant flare occurs, we'll be watching. Our gamma ray satellites will detect the initial spike. Our X-ray telescopes will track the oscillating tail. Our radio telescopes will search for the expanding debris cloud. And from the data we collect, from the photons that cross the galaxy to reach our instruments, we'll learn a little more about the densest matter in the universe, about the strongest magnetic fields, about the fundamental laws of physics that govern everything from the smallest subatomic particle to the largest cosmic structure. That's what happens inside a magnetar flare. It begins with a whisper, a slow accumulation of stress deep inside a dead star. It builds for months or years, invisible, silent, patient. And then it ends with a scream, a burst of energy so violent that it reshapes the magnetic field of the star, rings the star like a bell, launches debris at 1/3 of the speed of light, and sends gamma rays racing across the galaxy to rattle the atmosphere of planets thousands of light years away. It's one of the most extreme events in the cosmos, and it all starts with a crack in a crystal 12 miles across, on a star that most people have never heard of, spinning quietly in the dark between the stars. The universe is full of things like this. Events of staggering power happening in places we can barely see, driven by physics that we're only beginning to understand. Magnetar flares remind us that the cosmos is not a calm or gentle place. It's violent, it's extreme. It operates on scales of energy and power that dwarf anything in human experience. And yet, from our little planet, orbiting our ordinary star, in our quiet corner of one spiral arm, we've managed to figure out what's happening. We've detected these flares from across the galaxy. We've built models that explain them. We've used them to probe the fundamental nature of matter and energy. We're small, and the universe is vast and violent. But we understand it. And that understanding, hard-won through decades of observation and theory and calculation, is one of the most remarkable achievements of our species. The next time you look up at the night sky, somewhere among those points of light, there's a magnetar. You can't see it. It's far too faint, but it's there, spinning slowly in the darkness, its crust straining under magnetic forces you can't imagine, building toward a moment of release that will briefly outshine everything around it. And when that moment comes, the light from that event will travel across space for years or centuries or millennia, and someday it will reach Earth. A whisper from a dead star, carrying secrets about the deepest nature of reality, arriving at a small blue planet where someone, maybe someone like you, will be paying attention. Thank you for joining me on this journey into one of the most extreme events in the universe. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the cosmos and the physics that governs it. The universe is full of extraordinary things. Magnetar flares are among the most extraordinary of all, and we're only just beginning to understand them. Good night, and sleep well, knowing that somewhere out there, a magnetar is quietly building towards something spectacular.